Hello, welcome to the video. In this lesson, we're going to be looking at section 11.2, where we're going to look at populations, samples, and hypotheses. So some of the things that we're going to look at is can we look at a sample set and first off, distinguish what is a population of a piece of data, what is a sample of a piece of data, and then be able to analyze a hypothesis for whatever situation that they may give us. So first off, we're going to talk about population and sample. Okay. So here they want us to identify the population and sample of this example. So the first thing we have to figure out is what does it mean for it to be a population? And what does it mean to be a sample? A population, by definition here, it says is a collection of all the data. All right, so it's a collection of all data that you want the information about. All right. So for instance, in this example here, it says in the United States, a survey of 2,184 adults ages 18 and over found that 1,328 of them own at least one pet. So the population that we're looking at is going to be all adults ages 18 and over in the US. Now, looking at a sample is a subset of the population. Because you're not going to survey everybody that meets that criteria, you are going to be looking at a sample set, a subset of this. So in this particular example, my subset is 2,184 adults in the survey. And then in this particular example, they're asking us to describe the sample. So our description of this sample would be that of the 2,184 adults, we can say that 1,328 of those adults owned at least one pet. And same thing would be like 856 of them don't own any pets. So that's kind of a description of the sample with respect to the population. Here, they're asking the same question as they want us to identify the population and the sample. So here it says to estimate the gasoline mileage of new cars sold in the United States, a consumer advocacy group tests 845 new cars and finds they have an average of 25.1 miles per gallon. All right, so population for this particular response is going to be the gasoline mileages of all new cars sold in the US. So that's the population. But again, they have a sample of this. So the sample of the subset of this is going to be that they looked at 845 new cars sold in the US. And the description of this would be that of those 845 new cars, their average miles per gallon was 25.1. All right. Here, they're asking us, says for students taking the SAT in a recent year, the mean mathematical score was 514. Is the mean score a parameter or a statistic? Explain your reasoning. So again, we have two different definitions that they're asking for, and we have to make a decision. So again, let's look at parameter. By definition, a parameter is a numerical description of a population. And a statistic is a numerical description of a sample. So the question is, are we looking at the ACT scores with respect to a population, or are we looking at the ACT, or I'm sorry, SAT scores, not ACT, SAT scores of a sample? So because the mean score is 514, uh, this mean score is, all right, yeah. So because they say the mean score is 514 and they're not pulling it out from a subset, we can say that this particular example is a parameter. Here, it says a survey of 1,060 women ages 20 to 29 in the United States found that the standard deviation of their heights is about 2.6 inches. Is the standard deviation of heights a parameter or a statistic? Explain your reasoning. Well, because they said they surveyed the 1,060 women, that is a subset of the population. Since it's a subset of the population, we are looking at a sample. Since we are looking at a sample, we are saying that the standard deviation is a statistic. All right. Last thing here talking about, it says you roll a 6-sided dice 5 times and do not get an even number. The probability of this happening is 1/2 raised to the 5th power, which is 0.03125. So it's like about a 3.1% chance of this happening. So you suspect that this die favors odd numbers. The die maker claims the die does not favor odd numbers. What should you conclude when you roll the actual die 50 times and get 26 odd numbers and 35 odd numbers? So it's 2 different experiments. Now, because the die maker's claim says that there is no favoritism, that means that the theoretical probability of you landing on an odd number is 1/2. Okay, because there's 1, 2, 3, 4, 5, 6. So there's there's 3 favorable outcomes, and then there's 6 possible outcomes in this particular situation. So 3 out of 6 gets you 1/2. So what we do here now is you are going to now assume that rolling an odd number is you have a 1 out of 2 chance of doing so. So you do your own experiment. So you roll the dice 50 times. By rolling the dice 50 times, you get now a experimental probability of rolling an odd number 26 out of 50 times. So that gets you like a decimal. So that's what, like 0.52 or 52%. So this is 50%. All right. The next one is 35. So now we got 35 out of 50, which is 0.7 or 70%. Okay. Now, what we have to make conclusions of is we are going to reference this chart here. So this is a simulation of rolling a dice 50 times. So if you look here, it says this is the proportion of 50 rolls that result in odd numbers. So here it looks like, they say that 0.52 is somewhere right around here, which gets you at, right, they talk about the relative frequency. So we get a relative frequency that is about, I would say, I think like 0.14, I guess, something about 0.14. And on the other side here, 0.7, that's not even on the chart. So it's almost close. It's almost close to 0. So what we can say here is by getting 26 odd numbers in 50 rolls corresponds with that 52%. With respect to the simulation, you have that relative frequency. I would say it's about 0.14. So in fact, most of the results are close to the 50%. So because the results occur by chance, you can conclude in this experiment that the die maker's claim is true. Now, if you looked at it with respect to example B, by getting 35 odd numbers in 50 rolls. That corresponds again with 70%. And looking at the simulations, because getting 35 odd numbers is highly unlikely to occur by chance, we can say that with respect to example B, the die maker's claim is false. And that is being able to look at populations, samples, and hypotheses. Hope this helps. Till next time.